So thank you for having me. My title is a little bit different than in the program, so I'm going to talk about one model as an effort towards completing quantum mechanics, what I've called the process algebra approach. Just by way of background, I'm sort of a jack of all trades in many ways. I do a lot of research in complex systems theory. It informs the sort of philosophical background to this approach. I'm an MD. I have fellowships in psychiatry and geriatric psychiatry, but I also have PhD in mathematics and in theoretical physics. You can decide whether I'm sort of a jack of all trades, master of none, or not. My own interest in this is noticing that modern theoretical physics has taken a decidedly anti-realist approach to questions of ontology, what Bell in his work termed romantic. The hidden variable theorems and related experiments have provided support for such views, but they presume that hidden variables and classicality must be non-contextual and follow Kolmogorov laws of probability. But this assumption is not necessarily true. There are examples appearing in psychology and economics, game theory, where we see non-Kolmogorov probability laws showing up. And the process algebra approach exploits this. The efforts to try and provide a language for completing quantum mechanics with a decidedly unromantic, what I call mostly non-local and partly non-contextual, relativistically invariant, but non-Kolmogorov theory of ultimate reality. And in this framework, quantum mechanics appears as an emergent theory. So quantum mechanics has proven to be highly successful as a computational theory, yet as other speakers and many people before me have talked about, it's plagued with seemingly endless ontological confusions. I wondered if it's possible that the dogmatic adherence to the use of the Hilbert space mathematically for the formulation of quantum mechanics has become a conceptual straitjacket limiting progress. I noted even von Neumann had expressed some doubts about the wisdom of the Hilbert space, albeit in a different context, but he once wrote, "I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space anymore." In the Hilbert space, the problem for me is that it conflates two ideas, an ontological notion in describing the state of the fundamental entity and epistemological in determining the probability of an observation leading to a measurement value. The standard way of decomposing a wave function in the Hilbert space is usually over some operator, generally Hamiltonian operator, and over some basis of eigenfunctions for this operator. But in doing so, one notices that the evaluation of the wave function at some spacetime point z becomes a sum of contributions from distinct ontological states. In a way, it's like building up a summary of an apple, an orange, a banana, and a pear, all mixed up into one state, or one point, which sort of gives you fruit salad, I suppose, but entangles the information from those multiple ontological states. The problem, of course, is when we measure relative to that operator, we always find the system in a single eigenstate. So how from all that entangled information do we manage to extract one definite value? An alternative approach is to recognize that the quantum mechanical Hilbert space is a reproducing kernel Hilbert space. So we may take the decomposition of the wave function one step further. So we can associate to each eigenfunction a unique discrete set of base points, and each base point a unique function from which the original function may be expressed as this sum. So on the base points, the value of the wave function now corresponds to that of a single eigenfunction. And the values of the remaining points are obtained through interpolation. Each base point thus represents a contribution to exactly one ontological state. Here the information...
I'm sorry, Dr. Sulis, we can't see your screen.
Oh, no? Still there?
Yes.
So in this way, the information is disentangled, but the wave function now becomes an emergent object. And that it follows from Fettinger-Grotjenic interpolation theory, which allows non-uniform distribution of basis points. Mathematically, though, it's more convenient to use sync interpolation, but that assumes that these base points are distributed on regular lattices. You can allow for small non-uniformity in the distribution, which adds another small source of error, so we don't lose too much. The beauty of sync interpolation, though, is that you can choose a single function, g, which is independent of the basis sets. So the wave function takes this form here. And now we see that the wave function is generated from a knowledge of the base set and the values of the wave function on this set alone. So that all of the information, all the physics can be determined just on this discrete set of base points. And the interpolation becomes a universal function. It's important that when you're doing this kind of interpolation to recognize that there are an infinite number of ways in which these sets of base points can be selected and from which the wave function can be constructed. So that at the emergent level of the wave function, information about the lower level, the so-called ultimate reality, is protected. We call base point sets giving rise to the same wave function epistemologically equivalent. And one use for us is that we can then develop heuristic representations for modeling this ultimate reality, since at the present time we don't have any direct knowledge about what might be this reality, what the physics might look like at that level. And one of the useful ones I found is notions from combinatorial games. Now, these base sets are discrete. Over the years, there's been several lines of evidence suggesting, too, that ultimate reality should be discrete, finite, and bounded. We have arguments from quantum gravity, from energy and momentum exchanges, the absence of divergences in physical processes and such. Another recent argument comes from Geisen and his group, who developed an extension of the Bell inequality, concluding that either you have a violation of the principle of continuity or you have superluminal signaling. So since at least special relativity seems to be very well supported by experimental evidence, I opted to allow for the violation of the principle of continuity. So again, focusing on a discrete ultimate reality. At the end of their paper, they said this gives further weight to the idea that quantum correlations somehow arise from outside space-time, in the sense that no story in space and time can describe how they occur. Same is true for the Bell experiment, where you have entangled particles moving in different directions. One of the fundamental assumptions of Bell in regards to hidden variables is that they are statistically independent. And he needs that in order to make assertions about parameter independence, outcome independence, and particularly how the expectation values get calculated. And it's that assumption which forces the use of Kolmogorov laws of probability in calculating the inequality, whereas one already knows that quantum mechanics is non-Kolmogorov in its structure. So you have a problem, too, that one knows that the measurement values obtained from these entangled particles are correlated both from the time of their origin to the time of measurement. So we're going to describe these with hidden variables which are statistically independent and uncorrelated. There's a question then, where do the correlations come from? And that seems to me to be a major flaw in most of the hidden variable theorems that rely on various inequalities. So, to preserve both the quantum character of interactions and the ontology and the specificity of measurements, and taking Geissen's quote at heart, this suggests that perhaps the ultimate, or the elements of ultimate reality should come into existence individually. They need to be generated, and interactions should depend upon the generation of these individual elements. We have a philosophical theory which can describe such a reality. That's the theory of process that Whitehead developed in the 1920s. He applied ideas from organisms to describing ultimate reality. Canadian biophysicist Robert Rosen echoed some of those ideas in a festschrift for
Yes.
home. He wrote.
This is another speaking. A já to neslyším, člověče. To, co říká, to jsou slajdy už.
Right. Can perhaps the other microphone get stopped?
Yes, Dr. Sosek, could you please turn off your microphone because now Dr. Sulis is presenting his lecture.
I have already stopped the microphone.
But I can hear him. So
okay, Dr. Sulis, please continue.
I'll try and go on. So, Rosen wrote, the basis on which theoretical physics has developed for the past 3 centuries is in several crucial respects too narrow and far from being universal. The conceptual foundation of what we presently call theoretical physics is still very special. Indeed, far too much to accommodate organic phenomena, and rather sarcastically, he also said, and much else besides. So, both turn of the century, end of the century, people were suggesting using ideas from complex systems theory and process theory and apply it to understanding what's happening at the fundamental level. There's some key elements to process theory to mention. One is the idea is that reality is emergent rather than static. A central notion is that of becoming. So it's very different from the static block universe idea that we traditionally have in physics. Processes are thought to generate these fundamental elements that Whitehead called actual occasions. These occasions have both ontological and informational aspects. And his idea was that some informational residue from prior occasions becomes incorporated into the next generation of occasions through the action of process in a non-deterministic fashion. The occasions themselves are transient. They arise, they linger briefly long enough to pass forward their information, and then they fade away. So within process theory, reality is configured as a transient now, which looks, as philosophers call, a compound present, formed with the current generation of actual occasions, which are moving their information forward through process, and the next generation of occasions, which are being created with the dissolution of the prior generation once the next generation is completed, and then it repeats itself. So as I said, he postulated that this notion of a transient now, very often when you talk about ideas of now, you get into simultaneity, and that comes back to special relativity, where it's usually argued that it's not possible to have any kind of simultaneous now. But there's another interpretation of special relativity which rather than asserting the non-existence of a now, one sees it asserting the non-existence of global frames of reference. So space-like separated events can exist but be unobservable, and I'd argue that observability and existence aren't the same concept. Something can exist even without our knowing about it. Wigner commented somewhat like this in general relativity, where he emphasized that the values of coordinates per se aren't meaningful. Having those frames of reference aren't meaningful. Now, the process algebra model that I put forward attempts to mathematize these notions of actual occasions, base elements that I've called informons. Each informon gets described in this fashion. So it's just a label, which is just for mathematical convenience. You have two components, which are extrinsic features, which are entirely imposed by the observer. One is a causal interpretation, which just associates each informant with an element in some causal manifold, and a local Hilbert space interpretation, which is basically their local wavelet contribution to the global wave function. There are two intrinsic features, a vector of properties, which is a partial function. These are inherited from the generating process, and then the local process strength, which is used for determining interactions between processes. And then finally there's the content set, which is also a causally structured set of prior informons, which has its own Minkowski pseudometric, and this is the set of information that's incorporated into this current informant. And these informons are thought to be generated by processes. In the model, they're transient. One complete generation forms a structure called the causal tapestry. The causal tapestry you can think of as a generalization of a space-like hypersurface in a causal manifold, except for its transient nature. All the relevant prior information is represented in the content sets. And for consistency, taking the union over all of the content sets of the informants in the causal tapestry will give you a causal set, which gives it Lorentz invariance. And to each causal tapestry, we can associate a global Hilbert space interpretation, which you can think of as the wave function at one particular point in time. The basic idea can be represented here. So if you think of the horizontal line as like this causal manifold, then our basis point, so our informans, the elements of our reality, are these points. Here, the straight line is just showing you where they're embedding. To each of these points, there's associated a local wavelet contribution, and the strength of the process or the strength of the wave function at each of these informons. The wave function as a whole is this emergent wave function obtained through interpolation. You can think of it as a scale issue. So at the emergent level, observers, macroscopic reality, in this model even microscopic reality, what one sees is this emergent wave function, but the reality underneath really are these discrete informons. And this is just to represent the compound present. So from that prior tapestry, with its initially generated wave function, the process propagates information forward, creating the next tapestry, and resulting in the next generated wave function. And from this you can see that you can associate each process with an operator acting over a space of tapestries. And the processes are in basically one of two general states. They can be active or inactive. the idea is that the processes themselves are independent of space-time. They generate the elements which give rise to what we observe as space-time. Each process gets associated with some partial function of properties which they will impose to these informans, these space-time elements. There are some characteristics of them that we can describe, such as the number of informans which are generated per round, whether they generate a single informant or multiple informans per time. That takes care of single or multi-particle situations. The amount of information that's being propagated forward. The number of informans generated in the complete generation. And the propagator, which is used to propagate information forward from the prior to the next generation of informans. They're thought to generate informans non-deterministically, and somewhat like a diffusion process. Interactions between two processes that are coupled together is held to take place at the point of generation of their individual informans. So they're generating these things sequentially, one cluster at a time, representing different entities. When the correlated or clustered group of informans is generated, that's the point where there may be an interaction between these couple processes that can result in various changes, and that interaction is going to depend on the compatibility between the processes and the coupling strengths. Within this system, measurement is viewed simply as an interaction between a system process and a specialized measurement process called an apparatus. I'll mention the sort of rough model for measurement in a moment. I'm not going to go into detail. People can read it in some of the papers. The specialized measurement process just demands some behavior to ensure that the outcome of its evolution is some kind of symbol, marker, sign that then we can subsequently interpret. So, going back to the previous discussion, in this system, yes, computers can do measurements. All sorts of things do measurements. And we don't have consciousness. The probabilities depend on the local strengths of the informans, and given the form below, one can see that the probability structure is in fact non-Kolmogorov. Real simple model, the path integral model, just to give you a little example of how one might do this. You use a four-dimensional sinc function. You assume the lattice structure with three spatial dimensions at Planck length and one temporal dimension at Planck time. You take a discrete version of the action and basically a discrete version of the Feynman propagator. And if you do the calculations, again, you can look at the papers for the details. You can see expanding the process strength backwards from this point to some initial tapestry, how information gets propagated amongst the various informans, and giving you a discrete version of the Feynman path integral. The important thing to note here is that as the amount of information being transferred increases to infinity, so it becomes complete, you get a good approximation to the path integral, and then if you allow the scales to go to zero, it goes over to the actual path integral and will reproduce the quantum mechanical result, at least in the non-relativistic case. Remember, I've said that in this model, the informons are finite and discrete. So this gives you a discrepancy between the wave function that the model will generate and the usual quantum mechanical predictions, which at least in theory offers the possibility of testability. There are several causes for discrepancies to occur: truncation, amplitude, aliasing, time jitter, space jitter, information loss. But a simple calculation, assuming that the process is generating roughly a number of informons per causal tapestry generation in the range of around 300,000, keeping it at Planck scales, you get a discrepancy between this estimation and the actual wave function of around 10 to the minus 98. So the accuracy is really rather high, at least for relatively simple wave functions. The process algebra is the mathematical framework in which we describe how processes interact. It's based, again, on the combinatorial game heuristic. There are three features to be considered. The timing of generation of informons, which can be simultaneous or sequential. The flow of information, which is exclusive, where different sets of informons have information that's separated from other sets, and free, where all the information can be shared amongst all the informons. So basically, processes can either keep information private or can share it. And there are three different ways that processes can interrelate. They can be fully independent, coupled or bound, but where the processes themselves, the states, aren't changing, or bound and interacting, where states can be modified. Mathematically, this gives rise to a number of operators. There's one, just a comma to denote independent processes, a dot to denote concatenation, which represents successive processes, and it's important to note that concatenation operation is non-commutative, and it's from there that one learns that processes are not capable of generating all properties that might be available to an entity. This is where you get a limited form of contextuality showing up. And you have 8 distinct sums and products, depending on whether you have the non-interacting or the interacting case. In applying this, sums apply to single entities, free sums to single states, such as describing a two-state decomposition, exclusive sums when you have distinct states, such as superposition, bound, as I said, describes couple processes not exchanging, interactive exchanging products, which apply to multiple entities, free products when you have distinct types, such as in boson-fermion couplings, exclusive products where you have same types, so boson-boson, fermion-fermion. And the difference between the boson and the fermion case is that you have the full algebra available to products of bosons, but with fermions, you have to take a quotient. You have to quotient out what is essentially a nilpotent subalgebra to take care of the exclusion principle. The way to think superpositions in this case is each state, if we look at just one state and see its generation, we'll get informons basically all carrying the same properties. But if you have a superposition, then informons will get generated, some which will contain properties of the first state, some which will have properties of the second state. Again, when you sum them in the usual Hilbert space, you see everything gets mixed up. Whereas in the ontology, you never have an element of reality which is a superposition. Each element of reality corresponds to exactly one of these states. So reality is never entangled, it's just the confusion that shows up in the Hilbert space representation that creates the problem. And this just shows you how you can describe all of these cases just using the process algebra formalism. And in each of these cases, you get no paradoxes, you don't get ontological confusions, and you generate the same measurement probabilities as you would get in the normal quantum mechanical normal Hilbert space formulation. Measurement, the idea is it takes place in a set of stages, no observers required, it's just a particular interaction between two kinds of processes. So you can imagine two processes which are statistically independent at some point in time, freely evolving. You can think of like a particle and the apparatus, but they're far removed from one another. The particle comes within the vicinity of the apparatus, at which point there arises a coupling between the system and the apparatus. As the particle enters into the apparatus, there's basically a rotation that takes place, or decomposition of the system process into sub-processes corresponding to the eigenprocesses of the apparatus, or at least eigenprocesses compatible with the apparatus. At some point in time, and it can get tested every single time that the system and apparatus informums are created, there may be an interaction or not. If there is an interaction, that will trigger off a cascade within the measurement apparatus that eventually leads to the production of some sign, which effectively records the measurement. And the probability of this is going to depend again on the local strengths, which, being non-Kolmogorov, will give the same result as in the quantum mechanical situation. And following that, you may have, because of the interaction and the system and the apparatus now moving forward, the system's now in just the single eigenstate. Now, in the case of non-relativistic quantum mechanics, when you're dealing with just a single particle, you can think of processes generating a succession of causal tapestries representing individual occurrences of informons who collectively, emergently, give rise to this emergent wave function, emergent wave. So you have an ontological interpretation of the wave function as generated within the process model, and particles then become essentially these correlated elements that form an emergent wave. So they have wave-like, but because at the fundamental level they are discrete, they're both discrete and wave-like, particle and wave-like simultaneously. What you see really depends on how you interact with them, or if you like, at what level you're observing them. Now, I've said that the processes generate the informants non-deterministically. So from a given causal tapestry, a given initial state, processes will generate different collections of informons, potentially giving rise to different wave functions. So if we're going to attempt to do calculations, we need to collect all of these different interpretations because they represent all the different possible evolutions. And we do that in terms of a process covering map, which is a set-valued map from any initial causal tapestry to give us these different possible wave function outcomes. What's important, though, is that in the limit, it's the amount of information being generated. As the number of hormones increases to infinity, as the amount of information transferred from prior tapestry to current tapestry becomes infinite. So in other words, as the knowledge fast forward becomes complete, then in the single particle case, this process covering map degenerates to a singleton. And then if you allow the Planck scale to go to 0, you'll end up with a quantum mechanical wave function. So the interesting thing in this particular model is that, again, quantum mechanics is seen to be an effective theory when you can take Planck scale to be effectively 0. And it's an emergent model. Where classicality comes in, there's still a lot of work to explore that, but the thinking is that it arises out of the complexity of interactions amongst the component processes. If you think of something as complex as a human being, you've got, trillions of cells composed of enormous number of particles, all of which are highly interacting, entangled. And it's a result of the complexity of the process interactions that we start to see classical behavior, rather than it being a scale issue. To deal with multiple particles, though, you have to go up to another representation. So to create the process covering map, you effectively use what's called the process sequence space, where you just map out for yourself all possible generation sequences. When you're looking at products, though, that's not sufficient for calculations. It's adequate providing an ontological representation, but to do calculations, you need to take count of all possible correlated sets of hormones from the individual particles. And you can't get that through these single generations. So instead you have to construct a configuration sequence space where you artificially extend the process sequence space, adding in compatible hormones and wave function values until you get a maximal amount of information, and then you build your PCM on that. And one thing this framework makes clear then is that the configuration space, at least the configuration space in the process algebra approach, is purely heuristic. It's not an ontological space. So I think it kind of ends the debate about whether configuration space is merely heuristic or ontological. The model that's being presented here has some parallels with a number of other models that have been presented over the years. It differs quite significantly, though, I think, in its use of the transient now, these hormones, and the interpolation to connect the lower level of discrete space to our usual continuous space. So I've suggested that the process algebra approach provides a nuanced mathematics in which we can move towards the completion of quantum mechanics, which is realist. In this model, ultimate reality consists of definite elements with definite properties, albeit not all properties. It's mostly non-local. Information, I may not have mentioned, and I should have, is propagated locally. causally from prior informons to the next generation of informons. So it is Lorentz invariant, consistent with special relativity. As I said, it's partly non-contextual. The informants definitely have properties that they inherit from their generating processes, but process concatenation is non-commutative, and processes can't express all properties. It's finite discrete. You have ontologically distinct states with no Schrodinger's cats. And it's finite and discrete, so you've got no divergences. It's not really a wave function collapse here. There are changes in processes that can become active or inactive as a result of interactions. You get an emergent non-Kolmogorov probability structure, even though you can describe all of this earlier stuff pretty much using classical language. And quantum mechanics arises as an effective emergence model. There are some problems. Right now, this is primarily mathematical. The next stage is trying to develop some plausible physics for this ultimate level, trying to determine what would be the correct propagators, what should be reasonable values for these parameters, how much information should be moving forward, how many informon reasonably should be generated, and can one couple that to observables like energy and momentum, mass. One suggestion is to relate mass to the depth of the content set, since math or presence of mass enforces subluminal speeds of transmission of information, and so on. And I will stop there.
Okay. Thank you very much. And I ask everyone to turn on the microphones, and I think it's a good time to ask the questions. So I guess I would like to ask the first question. I'm not sure that this is a kind of right question, but is there any relationship between occasions in your description and the Gardens of Eden, which were Dr. Hooft was referring yesterday?
Well, it would be quite possible, as I said, because of epistemological equivalence, you can potentially generate these informons in a myriad of ways. So it's quite possible that one way to do that might be using a cellular automata model. I've not explored that, but there's nothing in principle, particularly in the sync interpolation model, where you're looking at a nice discrete lattice. That's a nice setting. And of course, in most cellular automata, information is propagating from local neighborhoods, very similar to what you're getting here. Garden of Eden states, I guess if you were to conjecture, might be like the very first. There's no particle, presumably, prior to its coming into existence. So there's no ancestors for that particle. So the initial informons, in that case, might well be considered analogous to Garden of Eden states. but that would just be conjecture.
Thank you very much. Is anyone interested to ask the question, please? Okay, so I thank you very much, Dr. Sulis, for your presentation.